Good morning. Today is the last webinar of NCS 2030 of this year, and we have Ying Guo, who is from NORCE, who will present her talk, Energy Management for Brownfield Operations. Go ahead, Ying, please.
Thank you, Tina. So I'm going to present our work within this topic, energy management for brownfield operations. The motivation of energy management is the focus at the moment. Let me see, how do I do the, okay, sorry. The vision of the NCS 2030 Center is, as you see here, to facilitate energy efficient multi-purpose utilization of the subsurface of NCS. Our work that I'm going to present is within the net zero emission production, which is a part of the center's research main topics. So today I'm going to introduce a LCA framework that we have been working on, which is relevant for the oil and gas field operations. So my presentation consists of the introduction of LCA framework, and also the framework we try to put into the context of oil and gas field operations, and then how we think we want to proceed with the energy management with example for water management. So short about LCA framework. LCA stands for Life Cycle Assessment. There are mainly 4 steps to perform an LCA analysis. It's actually a very well-established discipline for how to perform an LCA. So the different analysis can be compared and can be concluded for different aspects. Firstly, is the go and scope. And second step is life cycle inventory. And third step, impact assessment, and then interpretation. So this is a very large framework, but we want to use the methodology, the inspiration, but fit into our purposes. So a short overview of these 4 steps. First, defining goals and scope. We need to really understand what we want to use this for. What is the application? What is the audience and definitions? And very important is to define the boundary, where we start, where we end for this analysis, and what is the purpose for that. We need to find the different categories for definition of different aspects. And then last but not least is the functional unit definition. I will explain a little bit more later. So here this cycle illustrates, for instance, the cycles normally start from resources and the processing of resources, manufacturing, distribution, and use, and end of the life. So it can go back also if we do the recirculating path. Second step is, this is the most important and very tedious step. It's a life cycle inventory, LCI, illustrated by this figure. For instance, we have raw materials. We start from processing raw materials, and then it's multiple processes, because most of the processes will require multiple raw materials. And then it's assembly toward your use, and it's a final product. Of course, every step will require energy, and then there is a end of the life, which is a waste. So if you see the left side panel illustrated with a t-shirt, so t-shirt with cotton, black. What we need in an inventory is actually a very detailed setup of each of the raw materials, processing, assembly, and so on. So here is that, well, we need cotton, fabric, black. So what does it take to make it? cotton, we need bleach, we need the different fabric and electricity will need it, and so on. So here it's a inventory of the resources needed to get there. So if you look at the impact assessment, so we know what we need, what we use, but we, in this particular example, see that each of the step will have a CO2 footprint. So that's only one of the many aspects we can analyze on the life cycle assessment. So each of the step will have certain amount of CO2 equivalent for this. And we have decided that the unit is how much CO2 emission per t-shirt. Now, the impact may have many categories, and we are focusing on the global warming potential, the red one, and the environmental cost indicator. That's what we want to focus on. The other categories could also well be relevant according to the need. It could be human toxicity, it could be radioactive, freshwater, marine, ecotoxicity potential, and so on. So these are less used, but there are very well defined unit and also database to acquire these indicators. So step 4 is actually interpretation. Now, we need to identify significant issues based on the LCI phase, the inventory, and the problem and the accuracy of the data, and how they were measured and analyzed, evaluate the study itself, and in terms of consistency and completeness. Completeness is very important. We need to include all the relevant elements and draw the conclusions. In our case, for instance, how high is the emissions of the product and services we are introducing, and what is the environmental footprint? Which methods will improve our operation within low emission goals, for instance? And then we can, based on this analysis and interpretation, provide recommendations from the conclusions. One aspect which is a more quantitative estimate, it's on the environmental impact. Here is illustrated environmental impact. It could be, if we do it properly, it could be from cradle to grave, the whole process from the raw materials, extractions and manufacturing and usage and so on. And often, and hopefully more often in the future, we're going to do the reuse and reuse of waste or reuse of the materials that we introduce for certain purposes in the future and recycle. So all these can be included. This is an important step, but it's a very comprehensive step. Anyway, so illustrate this LCA for CO2 EOR. This is a published data, published paper from I think it's Dakota University Energy Research Center. Very simple setup, which is fit to this particular purpose. The boundary is set very limited, not from the cradle to the grave, but rather in a limited steps. So it starts with coal mining for energy production. But coal mining, we know the coal-fired power plant will have emission. So this coal-fired CO2 emission is captured to supply CO2 for field applications for EOR purposes. So here, some values are acquired for this particular purpose. This case is from the US. So we see the values used like 60 kilo CO2 per megawatt hour needed to produce energy, and how much CO2, 11,000 kilo, 1 ton kilo per megawatt emitted. And then this CO2 is captured, and how much CO2 captured energy is needed for that. And then transport will cost, transport of CO2 with pipelines will also cost certain, but it's not that much, as you can see, only 1 kilo approximately CO2 emitted per whatever the CO2 transported. And then it's CO2 EOR operations. Here it gets more interesting for our purposes, which is called gate-to-gate. So what is the CO2 used on board in the operational fashion? So the injection and production and so on, which is in this study not properly analyzed, but this is what we actually need in the future. I'll show you why. And then CO2 EOR will create hopefully incremental oil, and this oil is going to be transported to a refinery and refined, and then it's going to be used, and there is of course a footprint associated with that. So this is an analysis that has been used for their purposes to compare with other production methods for producing oil. So here, for instance, it uses US domestic production, which has about 80 kilo per barrel of CO2. No, sorry, that's cubic. So 500 kilo CO2 equivalent for barrel of oil. And then it compares with other number of methods. So if it's ratio 1, it means it's the basis. And you see the other methods, shale mining and shale in situ, it's a factor of 2, meaning that it has a double CO2 emission. But for the CO2 EOR purposes, the last two cases, the result is the ratio is much less than 1. It means that the oil produced with CO2 from coal-fired plant, captured from a coal-fired plant, is beneficial as compared to the conventional domestic US production. So this is a way to use analysis of a life cycle to compare different methodologies. And we want to implement in our center this methodology for the operation on the matured and brownfield operations. So we have started to set up a LCA framework for this particular purposes, and we selected the water management as the focus. So why is this area interesting? Well, we know that the Norwegian continental shelf is quite matured, and from this figure you can see that the red bars are the oil production from 2000 till 2023. It's now decreasing, quite stable at low level, but the water production you can see here is doubled of the oil production almost. At the same time, we also have a lot of water injection. Water injection has been used as the most important methods to optimize the oil production, either by energy conservation or sweeping of the oil from injectors to producer. So, and at the same time, we know that water injection is one of the most energy intensive operations. That's why to look into the energy related to water management is very important. So one way to reduce energy use by reducing the water injection and water production is a water diversion, illustrated with this figure. Here you see that water turns to break through from the injector to producer along the highways where the permeability is high, and you see the left behind oil in these squares, that the water swept area tends to have a lower remaining oil saturation, but the unswept areas is actually the target for water injection. But these highways needs to be stopped so that the water can sweep the unswept areas. Maybe most of you know that there is a very nice SNORA silicate pilot for deep water diversion. And you can find the information from this paper, SNORA Conformance Control, Impact on Oil Recovery and CO2 Footprint, which was recently published by Felix and his co-workers. Here you see that there is a history of the SNORA from October 2011 and to the October 2019. During that period, in October 2013, the silicate pilot was performed. It has 3+ months of silicate injection with a 4% sodium silicate solution, and it has a density 1.4 as compared to water. The total injected silicate is about 10,000 tons because of the high sodium silicate solution concentration. And we try to predict or calculate roughly the CO2 footprint of production of this huge amount of silicate, which equivalent to about 1.2 ton per CO2, 1.2 ton CO2 per ton of silicate. So the total emission is about 12 kiloton of CO2, and then total water injected, so after the 3 months of injection, the monitor data shows that the water cut has been reduced from the initial about 98% to with about 3%. And the total water injected is reduced by about 5 million tons in the following 5 years. That's where you see the history from 2013 to 2019. And also there is an incremental oil, about 400,000 barrels during the 5 years. So that's the outcome of the pilot itself. Now, if we look into the simulation model used for this pilot, we looked into the history match of the model itself, both before the injection and after injection. And we so you see, this is the red curve of silicate injected. That's a history match. And then we say, if we didn't do the pilot, we just let it go, what would be the situation? It will be the blue if we continue injecting seawater. So the beneficial is very clear. So based on this case, we say, okay, let's look into the framework, and if this framework may help identifying the energy and emission footprint, CO2 footprint. So here is a framework we have put up to see the core process, which is what's happening on the platform, which is mostly, of course, the operations on the surface, but also including the treatment of water injection and back-produced water and potentially discharge to sea, which will have an environmental footprint and so on. But in addition to the core process, it could also be electricity imports that will increase or decrease the emission. It could also be chemicals used that is brought on board from other sources. Of course, there is emission from the product itself. So if you look at roughly the CO2 footprint and energy for SNORA case, so here we have, for instance, we have a 3% reduced water cut for 5 years. That could be mapped back to about 9 kilotons of CO2 reduction because reduced water, less treatment, and so on. And at the same time, we saved 5 million injection water, equivalent to 20 gigawatt hours for the injection operations. This number is very roughly, but it represents probably the high energy need for water injection. And then we can see that the CO2 emission from the product of 400,000 barrels, 500,000 barrels, that's incremental oil, and that represents 3,000 gigawatt hours of the energy carried by this oil. So obviously, 20 gigabyte saved, and then it's the incremental gives a lot of additional energy, which is beneficial. And then we look into the emission because of the operation. So silicate, we have a production, injection operations, we have a production of the chemical itself, and so all these add up to CO2 emission. For instance, transport of a huge amount of silicate from the production location to offshore represent a big CO2 emission as well, and injection itself. So, but these are the important input in order to calculate the energy spending. What we don't have is actually the energy on board, the detailed calculations. So we don't know how much really turbine is, performing to inject the additional chemical, and afterwards to reduce the total energy to reduce the injection water and reflect it in energy saving. So that's why we started looking into the way to estimate the energy saving because of the silicate injection. Recently, we got this eCalc that we want to explore. So this is where we are right now. We also think the way to use this framework, if we say we didn't use silicate gel for the treatment, but we rather use associated polymer. So we use the model for different cases. These are the figures show that we run many different cases and look into what is the gain of additional production, what is the energy that is needed, which is orange bar, and blue is gain of the oil. We compare to see silicate has this performance I just showed you, but the polymer has another performance. Polymer uses much less chemical with a longer injection time, but the total, if we calculate roughly what is the incremental of oil and what is the reduction of the water injection, you see we actually have a different energy saving on this. So this is a way to compare different cases using this framework. So energy management for water management is with the, I think the clue is actually eCalc part to really calculate the energy saving on board the platform. So what is eCalc? eCalc is an open source software to perform energy and emission calculations by integrating data, knowledge, and future plans from different disciplines, subsurface versus process at the top side. The main idea is to really have physical data to relate the production performance on one side, they come from the reservoir modeling, to the topside performance and description. So this is slide for you who are interested about this open source code. I won't go into the details, but it's available there. You can see the GitHub link for this. So eCalc allows us to really put up the surface energy situations, I would say, by something called Sankey diagram, which is showed here as an example. A very typical on board and the platform, you have turbines, which is green turbines, to produce energy to generators. Yeah, generator will drive compressors for gas and pumps for liquid, and different miscellaneous for the platform operations, all the way from warming, cooking to whatever needed of energy. So, and of course there is a fuel and flare of gas, and all that is included in eCalc calculations. When this is set up, it's possible to calculate the energy spending on each of these elements. That's important for us to know which components represent the largest energy consumption and can be optimized. The things that we don't normally think of is actually the non-linear behavior of the energy producers, which are turbines. It could be fuel diesel-driven producers as well. And you see here the turbine efficiency as compared to the production in terms of megawatt is not linear. That means that if you need a, say, lower energy, actually the turbine is performing less efficient. So it doesn't mean you actually save energy. Similarly with compressor, which is more severe. You see the green line here is efficiency. So if the throughput of injection volume, production volume, and so on requires different compressor with the rate, the efficiency changes. So the important thing is to be at the top all the time to save the energy or to have the maximum performance. So these are the operating windows for these two different compressors. And pump chart is the same behavior. See here, you have the green efficiency is not linear neither. It doesn't say that the higher the injection rate, the higher the energy, because efficiency is, there is a top here. Now, the input to ECalc are all these curves that will calculate where you are, what is your need, and try to optimize the energy production and energy use based on these input curves. The input to relate to reservoir performance is given by the production and injection data, for instance, from simulations. It can also give input for reservoir pressures. So that is the important part to relate the reservoir performance to the topside performance. I think the challenge is really the barrier, to tear down the barrier between the surface and subsurface parts, which is currently subsurface is reservoir engineers and topside is process engineers. We need to collaborate more in these areas. So looking at what ECalc can give us, here there are two cases actually we have tested. One case is just the Sankei diagram that I showed earlier. You see different consumers of energy, which is there are two installations. So the orange and gray are the main consumers, which give the main energy CO2 emissions because they are related to the energy spending. But if you look at the right-hand side, you see the other consumers in more details. So here, because the emission is related to production, consumers is actually spending of the energies. So you see here, the orange and gray are gas export, a main consumer, and the rest is a water injection, the green, and there are other fixed production load and the pumping spending, orange. So these are smaller energy users. So these are not directly related to emission because emissions is really related to production. Of the ECalc also gives us a flare, you see at the top here. And if we run another case where electricity is phased in, of course, we save a lot of CO2 emission. If you see here, the scale are different. But the energy spending is not very different. Of course, we still need the energy to do the same operations. So this is a sort of tools I think is very powerful to help us to optimize the energy or to minimize the energy spending and i.e. also CO2 emission. So this framework, I think it's due to be tested for real case studies where we can use the necessary inventory data and necessary environmental footprint impact, and in addition to the ECalc to help us to put up different cases with different energy and emission footprint. So by conclusion, there are a lot of challenges. We have just started and we have hopefully planned to use that for different field cases. but we do have, firstly, we need to implement the LCA to bring the engineers and surface and subsurface people together, and to implement the tools, and to establish some kind of quick indicators for energy and emission. Of course, the main challenge is always lack of public available database for inventory and production reservoir models that we need to predict to link the energy spending to the subsurface performance. And the variation is obvious case by case. Different platform will have different setups and also reservoir performance. The quantification of the effect depends really on the historical information to match our models, both subsurface and also surface, with the model calibration of this energy setup. So it's very important to have all these tools and data all together in order to have a really efficient tool for energy management. So with that, I thank the NCS partners and observers for this work. That's all. Thank you.